Welcome everybody to Calculus BC. In today's episode, we will be discussing an integral review. And so we learned integrals in the second part of Calculus AB. That was what the B portion stood for. It was all about integration, which was the antiderivative, the reverse process of deriving a function. We were able to find out what function we had given its derivative. And one of the consequences of learning this was we were able to extrapolate that one of the mechanisms for integration is that it allows us to find the area between a curve and its own axis. And so just the accumulation of space that exists between the curve and the axis is what we're able to find. Today we'll be doing a bunch of different integral problems, and we'll just kind of get our integral gears going, and we will go from here. So let's go and take a look at what we've got. I'm just going to start off with number 8 right out the gate. I'm going to start off with an integration technique that you guys are hopefully familiar with. X squared over e to the x cubed dx. And with this one here, what I'm seeing in this integration problem here is I'm seeing a function which is the x cubed. I'm seeing its own derivative on the outside. That leads me to believe that we're dealing with a u sub. All right, substitution, reversal of chain rule. And so my u is going to be my x cubed because I see its derivative. Du is going to be x squared dx. I'm hoping these things look familiar. And so actually, I apologize, 3x squared dx. And then so from here, when I go ahead and get the x squared dx by itself, I'm going to go and divide out. So I get du over 3 equals x squared dx. From here, what I do is I see this linkage right here, the x squared dx, and I replace them with du over 3. So that integral becomes the integral of 1 over e, not to x cubed anymore, but to the u. And then that dx right here is going to get replaced. The x squared dx is going to be replaced by du over 3, or in other words, 1/3 du. Now I'm slowing this down a little bit for this particular problem because we're just coming out of the gate. However, I normally kick those constants on the outside, and you should get used to seeing me do that very often. And here we go. From here, I'll algebraically manipulate it one last time to get 1/3 e to the negative u du. And now I can go ahead and go again. So I can go ahead and say this is going to be e to the negative u. And I'm actually going to reverse chain rule out of -1 right here because of this negative bit on the outside. There's a way I could have done this from the beginning, but I decided not to. But this 1/3, this 1/3 is going to come along for the ride, and he's going to get a plus c. And so I have to figure out what u was from the beginning. Well, that's going to be x cubed. So I'm going to go ahead and say -1/3 e to the negative x cubed, and then with a plus c right over here. So here we go. That is going to be our first integral out the gate. And so from here, let's move on. I'll just choose another random one. Here's an integral application. 16. It says, what is the area of the region completely bounded by the curve of y equals negative x squared plus x plus 6 and the line y equals 4. So this is kind of an area between curves problem here. And so I'm going to go ahead and set them equal to each other first. And the reason why I'm doing that is because by setting them equal to each other, I am going to be finding the limits of integration. So I'm going to go and subtract 6 from either side. And now I'll go and just move the x's over, so I should get x squared minus x minus 2 is equal to 0. So if I factor, I'm going to get x and x here. So I'm looking at, looks like a -2 and a +1, so x equals -1 and 2. These are now my limits of integration from -1 to 2. Now from here, if I know these graphs appropriately, I'm pretty sure it's going to be the parabola up top with the line on the bottom. So what I'm thinking is the parabola is going to be first, and the 4 is going to be on bottom. I'm not going to forget my dx there. So I have the integral from -1 to 2 of negative x squared plus x plus 2 is equal, not equal to, but dx. And now that is going to equal negative x cubed over 3 plus x squared over 2 plus 2x. And that's going to be evaluated on the interval from -1 to 2. So let's go ahead and evaluate this thing and see what happens. So there's no way around this thing. I'm gonna have to punch all this stuff in. So there's nothing I can do to make this easier. So I'll go and just go negative 2 cubed over 3 plus 2 squared over 2 plus 2 times 2 minus the entirety of, here's where I got to be careful plugging in negative values. So negative 1 cubed over 3 plus negative 1 squared over 2 plus 2 times negative 1. So let's just take this nice and slow and make sure that we are evaluating this correctly. This is going to be negative 8 thirds plus, looks like 4 over 2 plus 4. This guy here is going to become negative 1/3 but positive, so I'll go positive 1/3 here. This guy is going to go plus 1/2 and then minus 2. Now I'm going to go and distribute the negative in, and I get negative 1/3 minus 1/2 plus 2. And then notice I haven't gotten any common denominators yet. I'm going to try and combine as many like terms as I can before I do that. I'm going to go ahead and call him 2 plus 4. So now I'm going to go ahead and say 2 plus 2 is 4, plus 4 is going to be 8. This 8/3 is going to combine with this guy to become minus 9/3 minus 1/2. So what's that going to ultimately become? This is 3. So that's going to become 5 minus 1/2. In other words, 4.5 or 9/2. And I believe that is one of the answers on that problem. So let's go ahead and move on to the next problem here. I'll be right back with some more board space. Number 25 tells us about the average value. So we have a function y equals rad x, and the interval is from 0 to 2. Now the word average value is really important because whenever I hear average value, I think about dividing the integral by b minus a, or multiplying the integral by 1 over b minus a, in this case 1 over 2 minus 0, finding the distance of the limits of integration and then dividing those from the integral itself. So from 0 to 2, I'm going to call them x to the 1/2 dx. That's going to get me 1/2, right? And that's going to get me 1/2. This is the 1/2 that I'm talking about. So then times, it's going to be x to the 3/2 times 2/3. Remember, this 1/2 came from the average value portion. So now the 2's are going to conveniently cancel each other out. By the way, this is being evaluated on the interval from 0 to 2. So what I've got is 1/3 x to the 3/2 on 0 to 2. Now this 1/3 constant, I would rather not deal with him, so I'm going to go and factor him out. And I get x to the 3/2. Actually, no, I'll plug stuff in right away. 2 to the 3/2 minus 0 to the 3/2. Well, that part's easy. That guy's going to go away. So now I end up with, looks like 1/3, and then this one can't be powered down, so I'm going to go and shoot him upward here. So that's going to be 8 to the 1/2. In other words, the square root of 8 over 3. If I really wanted to simplify him out, I could call him 2 rad 2 over 3. And I believe that is one of the answers. So hopefully this stuff's coming back. Average value is pretty important. It shows up somewhat regularly on AP exams. There's usually a question regarding it. 36, integral from 0 to 3 of absolute value of x minus 1 dx. So one of the most common misconceptions about a problem that looks like this is that you have to break this absolute value into a piecewise function, which actually would totally make sense considering that we emphasized the idea heavily in derivatives. But in this case, it might help to see this a little bit differently. Every one of these functions has a graphical component to it. And this one here, the reason why it's so important to see it this way is because now if you're going from 0 to 3, you could call 3 here. And remember what we talked about, how using integration was a means to finding the space between the curve and the x-axis. Now we've got the situation where we can do just that, but using only our integrated 2 skills. Rather than making 2 separate integrals with 2 separate functions and then integrating both and evaluating the integrations and then adding them, the answer to this rests on your ability to do 1/2 base times height twice. So the area of the first base is going to be, or the distance of the first base is 1. Its height is going to be what happens when I plug 0 into this function. So I'm going to get the absolute value of -1, which is 1. The distance here is 2 for the base. His height is going to be what happens when I plug in a 3 into the function. 3 minus 1 is 2. Absolute value of 2 is 2. So now from here, that's going to be 1/2 plus 4/2. Notice how I didn't reduce anything. I'm going to get 5/2 there. So when it comes to absolute value, please don't think too hard. Don't think you have to make a piecewise function when it comes to integration. When it comes to an absolute value, just draw a picture of it. Oftentimes that will take you to where you need to go. So I will be back with the next problem in just a second. The last problem here is number 74. It's going to be d over dx of the integral from 0 to x of cos 2 pi u du. Now, whenever you see this action happening here, the derivative on the outside of an integral, second fundamental theorem of calculus here, at least according to our old book. It's the second fundamental theorem of calculus, which means I'm just going to go and replace the u with x. So I should get cos of 2 pi x. And that's it. No plus c, no nothing. That one's probably one of the easier questions you could get. I'm going to go ahead and cap the lesson right here. If you guys noticed, I did not do a differential equation. I did not do a volume of rotation, nor did I do a cross-sectional volume. That is because we actually have our own lessons for those, and so that will show up in another video. I purposely skipped those, so don't worry about it. If you're wondering, hey, well, where did the volume of rotation go? We will definitely be tackling on volumes of rotation across both axes, hollow and solid, as well as something else. But for now, just a way to get your feet back into the pool for integration, and hopefully at this point you are feeling a little more comfortable with your calculus knowledge. You are reconnecting with that past calculus self. So welcome to the journey. I'm looking forward to the next 12 weeks. It's going to be a lot of fun. Buckle up, and I will see you all in the next episode.